Good afternoon and welcome to Algorithms and Data Structures today. So in the last lecture, 2 weeks ago, we started with recursion and concretely we saw what recursion is, started with this factorial example here. And recursion really helps us that we can express a function in terms of itself. And we looked at a few examples. We looked at the stack trace, and then we looked at a sequential search, which is O of n. But if we assume the data set is sorted, then we can solve the search problem in O of log n. And we describe the binary search as a recursive algorithm. You can also convert this to an iterative algorithm, but from a perspective of recursion, we can probably express this most easily initially. And the concept we apply here is divide and conquer, because when we have a large problem that we are unable to solve directly, maybe we can break it into smaller problems, solve those smaller problems, and then put it all together. So, and divide and conquer, we saw in binary search. Today we'll finish recursion, and we will also express quicksort and merge sort, which we're discussing later today in terms of divide and conquer. We saw the towers of Hanoi as a toy example for divide and conquer, and we see actually if we express this in terms of divide and conquer and use recursion, it's just a few lines of code. We saw the pros and cons of recursion. We saw recursion can be slow if implemented the wrong way, but there are ways to speed it up. We discussed this and also potentially how to get rid of some recursion. We can always, in theory, convert between iteration and recursion, but sometimes the one or the other is probably more intuitive depending on your problem. And then we wondered how we can determine the complexity of recursive functions. And for that, we looked at recurrence relations of how the time or the amount of primitive operations subject to n would evolve. And these recurrence relations, we describe how the function relates to itself, or the algorithm relates to itself in terms of n with the recursion. And we try to find a pattern in the recurrence relation and then solve this for k and plug in k into our term from before, into the pattern. And what we aim by solving for k is that when this recursion comes to an end, so when we have the edge case, when in this case here we would only have one example left. And then we plug in k, and then we simplify the term and then apply our O framework to it. And eventually we get the O complexity for binary search. We've seen another very general pattern of an algorithm that we will see more often in this course. Also today, we found out how we can solve this recurrence relation and determine the algorithm's complexity. And there were a couple of further exercises in case you're curious to solve more recurrence relations. Did anyone attempt solving these additional ones here? If so, maybe send us a thumbs up, or if you have not, send us a thumbs down. I'm just curious if anyone looked into those ones. You know, someone did. And we have the solutions in here in the slide deck. We also saw this list of common recurrence relations, like this one we had anyway done for binary search, or this one here was the other one we did in detail. And there are more, and you can try to solve them and see if you get the right solution. This one here is another quiz that maybe some of you have attempted or not, but I've started discussing this with some students in the lab. So if you're curious about this solution of this one here, maybe just come to one of the lab sessions. Concerning the lab, we have this course worksheet, and the students I saw today in the lab, they had already finished the work on recursion here, which is good, or most of them did. I had anyway uploaded a video 2 weeks ago on the weekend where I discussed problems 10.2 and 10.3 in detail with some additional thoughts. Who of you watched that additional lab video that I recorded? So maybe again, Send a thumbs up if you have, or a thumbs down if you have not. Hope this gave you some more insights. Yet, what I did not show in the video is how to determine the running time complexity of this one here. So you need to think about the recurrence relations of how the size of n changes through the recursion and then solve the recurrence relation. For this one here, this is the same recurrence relation as for binary search, and that the solution is O of log n. Now, solving recurrence relations and then determining the running time complexity is something that is maybe not that easy to some of you. So we do another vote here. If you feel solving these recurrence relations, finding a pattern, determining the running time complexity, if this looks all easy to you, maybe a green reaction. If you feel it's not that easy, or you still need some more practice, maybe send a red reaction. So I only see red reactions. Yeah, and that's what I expected. You still need to know how to solve these recurrence relations. So, and there's plenty of practice available here in the slide deck as well as in the coursework. Yet, we will now see one approach that is called the master theorem. And with that approach, we can solve a certain type of recurrence relation much more easy using a certain approach. So the idea of this master theorem is it's sort of a unifying method for solving recurrence relations, and not every possible recurrence relation, but at least some of them. And it's more like a structured approach of what we need to do rather than trying to find a pattern and so forth, because finding this pattern may be, again, quite challenging for various recurrence relations. And maybe for some of them, we can use this master theorem. So the master theorem does the following. We have a recurrence relation as before, that is T of n, and if its pattern matches, or if the recurrence relation matches this pattern here, then we can use it in the master theorem. And what we have here is, so we have T of n, and then we have T of n divided by b. So if the recurrence relation has a component where we divide n by b, which is a constant factor, plus we have a factor in front of that recursion, which is a, which is also a constant, plus there is some extra work that can be described by a function f of n. If our recurrence relation falls into this pattern, then we can use the master theorem to solve it straightforward. We've seen this before, that, for example, n got divided by 2. A could be 1, for A is the number of subproblems. If we just have one subproblem, A1 would be A. However, if we branch out to 2 subproblems, which we had also seen in the recurrence relation, then A would be 2. Plus there's some extra work, f of n. And n is again the input size. So some of the recurrence relations we saw, they fit into this pattern, some don't. Those that do can be solved with the master theorem. And the master theorem also assumes that the base case of T of n is theta of 1. So we've seen this before. So simply that there is some constant time as the base case. And we would also assume that we would assume that this base case appears when n is less than some threshold. For example, for T of 1 or T of 5, whatever, but some threshold that is not subject to n, but sort of maybe a constant. And we've seen this before, like we said, T of 1, or T of 2, whatever. And then what we need to calculate is a value that is called C critical. And that's the so-called critical exponent. And with that critical exponent, we want to determine how this work for splitting and recombining relates to um, the work that is done in the recursion, because here we do some work, plus we have some work for splitting eventually into multiple ones. In multiple, or saying one, the recursive call, or multiple ones, this is the work for splitting, and we have work for recombining when we put the results together, but also work is done in these recursive calls. And we need to figure out how that work relates to each other. And um, this is determined by this critical exponent, C critical, which is log B of A. Remember that n gets divided by B, and the factor of the number of subproblems is A. So the logarithm B of A is the critical exponent. And when we want to see how that critical exponent relates to this work, f of n, there are three cases. And based on these three cases, we need to do something different. And but overall, this is still much easier than trying to solve the recurrence relation manually. What you can also interpret is, what does log B of A actually mean? So A is the number of subproblems. So if I want to calculate log B of A, I can calculate this by log A divided by log B. And A is the number of subproblems, and B is the relative subproblem size, because we have the problem and split it into a smaller problem. So this B is the relative subproblem size, and A is the number of subproblems. And now we need to determine how this work f of n relates to the critical exponent. Maybe you are wondering how to remember all of this. And I have not talked too much about the exam in this course yet, so I'll probably mention this now briefly. Who of you has already looked into past exams? Maybe thumbs up or thumbs down. I know my teaching assistant, Melton, she discusses past exams in the tutorial sessions, and you can find all the past exams in my Nextcloud. So this is, for example, the exam we had last year. What is exactly in the exam doesn't matter for now, but what the exam says is the kind of tools you can bring. You can bring a calculator, which is any kind of calculator of which you can do fractions, sine, exponential functions, and this kind of stuff is fine, but you're not allowed to bring a computer algebra system. So don't bring a calculator that you could program or whatever. We don't want that. So a non-computer algebra system calculator, plus you can bring a one-sided handwritten A4 note sheet. So it's up to you what you write on this A4 note sheet on one side by hand. Maybe we would put the master theorem and its rules on it, because you may not remember that, and you could write this plus a couple of other things on this note sheet. So we're not looking into last year's exam. There's still more content to come, but bear this in mind that the note sheet could probably be quite helpful also with regards to the master theorem. Now, the first case in the master theorem, because now we care about these three cases, how does the critical exponent relate to the work in f of n? So the work f of n is the work for splitting and recombining, and the work in the subproblems, that's what's described by the critical exponent. And remember that we said here the work for splitting and recombining is f of n. So we wonder, how does this f of n relate to the critical exponent? And case one addresses where the work in the subproblems is more than the work for splitting and recombining. So the slide says the work for splitting and recombining is dwarfed by the work in the subproblems. So most of the work is done in the subproblems. If you see this as a recursion tree, you would say that tree is leaf heavy, because most of the work is done in the leaves of the tree, not in the work for splitting and recombining. And if we say that our function f of n is O of n to the to the power of c, where c is obviously a constant. So that means f of n is some can be described by some polynomial in its O complexity. And we say that this power of c is less than c critical. That would mean that the work done for splitting and recombining in the f of n is outnumbered by the work in the subproblems. And the work in the subproblems is described by c critical, the critical exponent. And if that is the case, then the master theorem says that our original recurrence relation is theta of n to the power of c critical. We are not deriving the master theorem. You can look up the original paper from probably the 70s or 80s when this was or initially derived. We will simply apply the master theorem in this course. And for that, I will now switch to my iPad and we can do an example together and see that this is actually less difficult than it appears to be. So you should be seeing my slides. So we'll do the master theorem. And case one. And we can have, for example, a recurrence relation. And all of this is also in the slide, step by step, including the solution. It's a times t of n half plus 1000 n squared. So you could solve this recurrence relation manually, but now we'll use the master theorem. And there are a couple of interesting observations. So we see this falls into our pattern before. So sorry, A is 8, then B is 2, and this here is f of n. So f of n is 1000 n squared. So we see that f of n is O of n to the power of c, where c is what? You can tell me this in the chat. So I have my f of n, and f of n is O of n to the power of c. So what would be that c then? If you see what c is, you can send it to the chat. Got a few answers. So c is 2. And to see that we are really in case one, we need to calculate the critical exponent. So c critical is log b of a. That means it's the log 2 of 8, which is simply 3. And that c critical, so the critical exponent, that one is greater than our c from above here, because 3 is greater than 2. So, and we said in case 1, the critical exponent must be greater than that c. So we can infer from the master theorem that t of n is theta of n to the power of c critical, and that is theta of n to the power of 3. So we've just found the solution for our recurrence relation. Just a couple of rules you need to remember, or you need to write this down for your note sheet, and then you don't need to manually solve the recurrence relation. And there'll be more exercises for you. If you look into past exams, you will see some more coursework potentially. All the recurrence relations we have done so far, you can also try to apply them to the master theorem. So all of this may give you extra practice. And everything I have just shown you is also available in my slides. So that's what I just solved together with you in the slide deck or on the whiteboard, and that's the case one example. Now, case two would mean that the work for splitting and recombining, so the work for this f of n, is comparable to the work done in the subproblems. That would be case two. And the master theorem says this can be also expressed if our f of n, so the work for splitting and recombining, is theta of n to the power of c critical times log n raised to the power of k. So this here means I take log n and raise that to the power of k. For some k that is greater than or equal to 0, if that is the case, then the master theorem says that T of n is theta of n to the power of c critical times log n raised to the power of k plus 1. So I did not come up with this. You can find this in the original paper on the master theorem, but we'll just treat it as a set of rules. We're not deriving or proving the master theorem. This would be too much for this course, yet it's a helpful tool set that we can use for the next recurrence relation. And we will look again at an example together. So for case two, we can look into an example. And we can say, well, this time this is t of n is 2 times t of n half plus n. Anyone remembers this recurrence relation from the course? If you do, thumbs up or thumbs down. So thumbs up. Yeah, we've done it before. We solved this manually, which was a little bit of work. It was for this more generic algorithm that splits into two subproblems and does some work for splitting and recombining. And we'll see this recurrence relation actually very often because it also relates to some of the sorting algorithms we'll be discussing in the next chapter. So we see A is 2, B is 2, and f of n is n. And we can calculate, first of all, C critical, and C critical, remember, is log B of A, which is the binary logarithm of 2, which is just 1. So C critical is 1. And when we look at our f of n, we can say, well, f of n is theta of n to the power of c critical times log n raised to the power of k. So f of n can be described by this, where c critical is 1, which we have shown from before, and where k is 0. Because if I plug in a 0 in here, so log n to the power of 0 is just 1, which would make this go away. So this would actually fit here for case 2, that this recurrence relation can be described by case 2, because raise log n to the power of 0 would just turn 1, and c critical is 1. So this would be just theta of n, and f of n would be then theta of n, because f of n is just n. So we have shown this, and now the solution is fairly simple, because case 2 told us before that then t of n is theta of n to the power of c critical times log n raised to the power of k plus 1. And this is, we just plug in the values. So C critical is 1 and k is 0, that means here the solution would be n to the power of 1 times log n raised to the power of 1, because k is 0 but plus 1. And so we can say this is simply n times log n, which is the correct solution, because when we manually solved this recurrence relation before, we also saw the solution is n log n. But with the master theorem, we don't need to find a pattern and plug in something into the pattern, but rather we follow this structured approach. What we have solved together is here in the slide as well. And I want to know from you, which approach do you feel more comfortable with? If you feel the master theorem makes all of this easier, maybe a thumbs up. If you feel the old way solving this manually was easier, that would be a thumbs down. I know it's a few new rules, but they can be followed, they can be written down, and you would just execute those rules. So I think it's actually far easier than trying this for some strange values in A and B, and you try to find some pattern and you just don't find it. Then when I see the total absolute or all of you feel the master theorem makes this easier. There's another recurrence relation that we've seen also in this course. For example, the one that refers to binary search or this fast power function from the coursework. We said the solution for this one is O of log n. And if you apply the master theorem to it, you will see it's theta of log n. I have the solution here, but you can try this during the weekend as a homework. And the good thing with the master theorem is also, it's not just a structured approach, but it gives us a theta, which is a much better, or which is much more insightful than an O. So the theta is actually very helpful. And this comes as an extra benefit with the master theorem. But try to solve this example at home. And there is the third case of the master theorem. And this case 3 is just the last possible case left, because we've said before that most of the work is done in the leaves, so in the subproblems. That was case 1. Case 2 said the work for the subproblems as well as splitting and combining is similar. And now the last obvious case is that the work for splitting and recombining takes most of the time and dominates the work in the subproblems. So we would say such a recursion tree is root heavy. And this one is slightly more complex, but again, it's just a few rules that can be followed. And what the case 3 would say is that the condition of f of n in relation to C critical must be that f of n is omega of n to the power of C, where C is greater than C critical. Because remember, C critical refers to the work in the subproblems, and C refers to the work in splitting and recombining. And so we would say f of n must have a lower boundary, n to the power of C, where the C is actually greater than the work done in the subproblems. But if you look in detail into the master theorem, then this alone does not yield much information yet, but we need to add another condition that the master theorem actually returns reasonable results. And a further condition would be that A times f of n divided by b, so we said A is the factor for the subproblems, B is the relative subproblem size. So that product must be less than or equal to k times f of n for some constant k that is less than 1 and for some sufficiently large n. And if we can find such a k, then t of n is simply theta of f of n. So the complexity of the work for splitting and recombining that dominates all the other work. So we would need to find such a k if this here holds true. And for that last case, I will also show you an example, and I'll switch back to my iPad. So I have case 3 here, and we would say t of n is 2 times t of n half plus n squared. So we've seen already this kind of stuff for 2 times t of n half in previous recurrence relations. But this time the work for splitting and recombining is n squared. So it far outweighs the other part. And I'll show you now why. So f of n is n squared and a is 2, b is 2. So if f of n is n squared, so we can say f of n, well, maybe wrong color, can say f of n is omega of n to the power of c, where c is what? I'm waiting for your response in the chat. What would be a reasonable c to show that this f of n here has a lower boundary of n to the power of c? Already got a few good answers here in the chat. It's actually fairly easy. So this works where c is 2. That was the easy part, and now we still need to calculate c critical and see if this is really case 3. And remember, c critical is log b of a, so log 2 of 2, which is 1. And this is actually less than c. C is 2. So we see this applies to case 3. But now we still need that additional condition and find a proper k for the inequality. Because remember, and I'll just write this down again, the master theorem demands that a times f of n divided by b must be less than or equal to k times f of n for k less than 1. And we need to see if we can find such a k here. And we know a, we know b, and we know f. We can plug in f because f is just n squared. So we can plug all of this in, and we can see that 2 times f of n half, because we know values for a and b, we can just write this out because f of n is n squared. So this is 2 times n squared divided by 4. So this was f of n. So I have this. And the question is this less than or equal to k times f of n? So k times n squared. And I can simplify this a little bit. So I can say I have a 2 divided by 4 n squared. So this would be n squared half must be less than or equal to k times n squared. So fairly easy because we have an n squared here and all we need is this k. So k would be a half. So since we have found such a k, we have shown we are actually in case 3. So we can fairly finish this now and say t of n is theta of f of n. which is theta of n squared. So that's the master theorem. I think it looks more complex than it is, and eventually it's just a few set of rules which you can remember or you can write down and you follow them, and this can make it far easier than solving the recurrence relation manually. However, for the exam, you need to know both methods. Sometimes in the exam, you may be free in choosing your method. Sometimes you may be asked using the master theorem. Sometimes you may be asked to solve it manually. So for the exam, you need to know both approaches. And what we did here is also in the slides. Yeah, you can use any k as long as it's less than 1 for which this would hold true. I just picked 1k for which this holds true, but you could pick other k's too as long as they're less than 1 in answer to your question. So the master theorem looks good, and I'll just go back to the early slide on the master theorem. The only thing is you need to bear in mind that your recurrence relation must fit into this pattern here. If it does not fit into this pattern, you can't use the master theorem. You can only use the master theorem for this pattern here. And there are a couple of examples when the master theorem, for example, cannot be used. If you have something like this, like a t of n is 2 to the power of n times t of n half plus something. This does not work because a needs to be a constant, and here a is not a constant because it's 2 to the power of n. Then we have this other one here. So t of n is 2 times t of n half plus n divided by log n. This part here is fine for a and b, but we always want to relate our critical exponent n or log b of a, and the critical exponent cannot be related to this one here because it's a non-polynomial difference. We could also think about a recurrence relation like this. T of n is 0.5 t of n half plus n. This also does not work because in reality, you have at least one subproblem if you have a recursion. You can't have half a subproblem. That does not work. So such a recurrence relation would be inadmissible as well, or something like this where the combination time is negative. Also, something like this doesn't make any sense from a computational perspective because we always add time in computation. We can't just magically go back in time. It doesn't work either. Or something like this, n times 2 minus cosine n times log n. This would regulate this, or it would violate this regularity that we have in case 3 around the k that we needed to find. So this wouldn't work either. What also would not work is if I have a recurrence relation, it would be t of n is, for example, t of n minus 1 plus something. We always require that n gets divided by b and not something gets subtracted from n or so and so forth. So, do you feel all okay with the master theorem? I know it's quite heavy, but eventually it's just a set of rules that we can apply. And all you need is some practice, and there's plenty of opportunities to get practice, like in the lab, the coursework, the tutorials, and yeah, you should also go regularly to the tutorials. Like there was a tutorial yesterday, and today we are finishing recursion. So the lab next week would also finish recursion. And there are now two things left that we will see in this recursion chapter. So what we started with was what is recursion, how divide and conquer works. We saw how we can determine the complexity of recursive algorithms, and we saw how the master theorem could be used for that. Oftentimes, when you have an introduction to recursion, there is a term called backtracking that you would hear about. And I briefly want to mention what backtracking is, and we will see we have actually done something like this for a long time in this course. So, backtracking is a general algorithm that would find all or some solutions to a computational problem. Usually, you would have some constraints and you would then incrementally build your candidates to the solution. And once we abandon a candidate, we would go back, so backtracking when we determine that that we simply need to abandon the candidate and we can't progress there. So we need to go back to a previous valid solution. Where you often would see this as a visualization is, for example, a maze where we try to go from the entry to the maze to the exit. And once we end in a corner or in a dead path, we would start to go back to the previous junction where it still worked. So that's backtracking, and you can visualize this with a maze. You can apply it to other search problems too. And it turns out we have done exactly that already in this course with our shortest path and lowest cost algorithms. They do something quite similar than backtracking because also certain candidates may not lead to a solution, but then we have other valid states from that have not been explored yet, and we have them in our frontier, so we take them and explore this. So it's what we've done in shortest path and lowest cost is actually quite similar to backtracking. Sometimes if you see backtracking as a tree search algorithm, we would sometimes say that backtracking traverses a search tree. So we have a search tree to search a problem in a graph, and we would then, if we traverse the search tree recursively from the root down, we would explore this tree in a so-called depth first order. The term depth first order is something we will see when we look into trees. So for now, you can just ignore this term and you can revisit it when we look into trees in one of the subsequent chapters. But in some algorithm classes, you may now see this very general backtracking algorithm. Here, we don't need to look at it because we've done something quite similar already with very generic algorithms, which are shortest path and lowest cost that we saw in the first week of the course. Now, the last topic we have left is dynamic programming. And we will see what dynamic programming is in this context. So dynamic programming is a term that often used in mathematical optimization methods, but it can also be a computer programming method. And dynamic programming essentially refers to simplifying a complicated problem because we break it down into simpler subproblems in a recursive manner. So sort of divide and conquer, but we want to solve these problems efficiently and we don't want to redo a lot of work. As you remember, when we started with recursion and looked at things like the Fibonacci numbers, this can very quickly become super slow because we do a lot of duplicate work when we branch out in the recursion. And we redo a lot of work that actually doesn't need to be redone. What we did as a quick fix in the course before, we used this decorator, this LRU cache decorator, and plugged this around our function that recursively calculates the Fibonacci numbers. And we will now see this from a more formal perspective, that there are actually two ways to do dynamic programming, which is top-down or bottom-up. And the top-down approach is actually what we had done before already with this LRU cache. But this time, we will not use the LRU cache, but we're going to build it ourselves. We're not going to use it as a decorator, but we will emulate this behavior. And the idea of this top-down approach is that it's something we can directly derive from the recursive formulation of any problem. And the solution will be straightforward because because we will use memoization. We've seen this term already when we looked at the LRU cache, and we will store results to solutions of the subproblems. And before we start calculating a solution, we already check if it's we check if it's already available in a cache. And if it is available in our cache, so we memorize it, we take it and we don't recompute. So that's exactly what our LRU decorator did, but we use the LRU decorator, and this time we will see how this can actually be done. And it's top down because we start with the big N of our problem and we start breaking, and then we start with it and we break it into smaller problems until these smaller problems are solved, or until we have something in the cache for smaller problems and we can read this and then abort the recursion at the step where we memorize. And we want to avoid recomputing things we had already done. So this means top down, we take the big N and start breaking it into smaller n's. This will be the memorizing approach. And after this, we will see a bottom-up approach where we don't break the big N, but rather start with small n's and keep combining them until we have built the big N. So it's the other way around. But we start with the top-down approach. And this one we will implement together. And I will share my slide deck, my interactive coding session with you. And you remember, I guess you can all see my my IPython session. And you remember what we did before was we implemented like the Fibonacci numbers and said something like, I'll just go back to the way, just quickly checking in my slides how we implemented it, that we use exactly something, the same approach. So we said if n is 0, we return 0. If n is 1, we return 1. And otherwise, we return the Fibonacci number of n minus 1 plus n minus 2. Are you all with me? Do you still remember this, what we did in the last lecture? Send some thumbs up or so. Okay, looks good. And what we did was potentially super inefficient because we compute n minus 1 and then n minus 2, and it's a lot of duplicate work. And then we put this decorator around it. So this time we don't use a decorator, but we use a global variable just to keep this simple here. And what we put in here is a memory. And the memory will be what we memorize. And we say the 0th Fibonacci number is 0. The first Fibonacci number is 1, and so forth. And later we will add new entries to the memory. And our Fibonacci number will look the following now. So what I want is I want to return what's in the memory for n. So our memory is a dictionary. We've seen dictionaries in the intro to Python, and I would just read out from what is in the memory. If I put in a 0, I would return a 0. If I put in a 1, I read out a 1. But this Fibonacci number for bigger N may not exist yet. So I first need to check if N is not in the memory. So N is always the key and the value is the corresponding nth Fibonacci number. So I can calculate the Fibonacci number and say, well, this is fib of n minus 1 plus fib of n minus 2. And intuitively, I would say something like, well, I will return this, but then I have calculated something and not stored it in the memory. So I will actually store this in the memory and say, if n is not in the memory yet, I will calculate fib of n minus 1 plus fib of n minus 2 and then store it in the memory and return it. But when I recursively build n minus 1, I will store, in order to calculate n minus 1, I need n minus 2 and n minus 3. So they will be ultimately computed, and later for that sum, I don't need to recompute my fib of n minus 2, but it will already be stored in the memory. And we can test this, and we can say, I want to read out fib of 10. And you remember, if I made n bigger, the Fibonacci numbers tended to become super slow. But now with this memorization, for which we used a decorator in the past, and now we didn't use a decorator, but we just implemented memorization on our own, I can also calculate like fib of 100, and it will run insanely fast because the memory keeps growing. And rather than using this LRU cache decorator, I just built my own memory. And I can also read out the memory now and see that all of these other Fibonacci numbers have been added to the memory. And I don't recompute something that I have computed already. And it's a top-down approach. So n is big, it gets split into two smaller n's. That one gets split again in two smaller n's. But once one of these smaller n's has been computed, it will be reused and I will not recompute it in some other branch of the recursion tree. So this approach just does what the LRU cache does, but I've just built the memorization on my own, and it's super fast compared to the manual approach from or to the normal approach without using memorization. So, are you surprised how easily I can speed up the Fibonacci numbers? If so, send some reaction. And all I needed to do was this top-down approach by maintaining my memory here. And that's the top-down approach. And as there is a top-down approach where we take the big N and split it into smaller n's, we can also start with small n's directly and then put them together until we have reached the big N and then abort. And that would be the bottom-up approach. So with bottom-up, we start with the small subproblems and keep composing until we have built the big N, and then we stop. And this approach of bottom-up and top-down is something you will actually see quite often in computer science and algorithms. So it not only applies to dynamic programming, applies to many other algorithm problems as well. And I'll show you how we can implement something like this. It will be a little bit more code, but in fact, it will run fairly easy too. So we can call this fib bottom up, for example, of n. And we can say, well, if n is 0, I return 0. And otherwise, I need to do something to get from 0 to n. And eventually, I build a current Fibonacci number that I will now incrementally compute. And I will then compose it and eventually return it. And for this, I have my Fibonacci number that is 1. But I need a helper variable that I call previous Fibonacci number 0, because if n is 0, we return 0. If n is at least one or greater, I need to do a little bit of more work. And so I need the previous Fibonacci number and the current Fibonacci number, and I will just incrementally add them together until I'm done, until I have reached n, and then return the current Fibonacci number. And so I say for I in range of n minus 1, you will see in a moment why it's n minus 1 and not 1, because I have these two helper variables and I keep adding them together, but I already have the 0th and the first one, and then I need to run to n minus 1 and not to n because of the two helper variables. Otherwise, I would add them one time too often together, and then I would have the wrong Fibonacci number. And I can now calculate my new Fibonacci number, which is the previous Fibonacci number plus the current Fibonacci number. But I may not be done here yet, but there could be more iterations. So I just need to shift all these values once. So my previous Fibonacci number will be overwritten with the current Fibonacci number, because that's now the previous one. And the current Fibonacci number is the new Fibonacci number I have just calculated. And if this loop runs once, these two get added, then I have one, and then the one from current fib would be moved into previous fib, and the new addition would be in current fib, and so forth. So I just keep shifting these values around. And with that approach, I can also calculate my 10th Fibonacci number, which is 55. And you will see that this also runs super fast, which wouldn't be possible just with the naive calculation. We can try to compare the running times, I would suggest. What we need to do is we have the memory from before. So I need to reset the memory from the top-down approach. And we can now run a time of the fib of, say, 100. And we don't do a time it because once we have written to the cache, that would be sort of cheating because fib was the top-down approach. And we saw this took like here 41 microseconds. And we can do a time of the fib bottom up. And we see this is some 12 microseconds. So also super fast compared to the naive one. You could compare this again for much, much larger ends. The only thing is the top-down approach would always read from memory. The bottom-up approach would always recompute because it doesn't have a cache the way we have built it, but rather it starts with the smallest Fibonacci numbers possible and keeps composing them until I'm done. But running this loop is also super fast. But we could try this again for a different Fibonacci number. So we can say fib for 10,000, for example. Well, the problem is here now we have reached the maximum recursion depth with the top-down approach. So we can say probably like 2000 on this system should still work with the recursion level. So this was 784 microseconds, and the fib bottom up for 2000. Here we will see it's like 223 microseconds. Probably a bit faster because we don't need the cache. We don't need any recursion, while with the top-down implementation from before, there was recursion. We just try to end it quickly. But here, with the bottom-up approach, we don't have any recursion because we just have the loop. But we need to recompute. So if I call this again, say fib of 2000, we see it reads out super fast from the cache because there is no further recursion. But if I run it again with the bottom-up, it needs to recompute, and then say for the second time, the cache here would benefit a lot, while for the bottom up, I'm recomputing from scratch and if I build, but I need more memory. And that's a typical trade-off I have to make between running time and memory, and this cache may get very, very big for a lot of Fibonacci numbers, or if it's not just Fibonacci numbers, but some other kind of objects that I'm unable to cache, I need to bear this in mind as well. So it's a trade-off you need to make. One student said that he finds the second one more understandable. Um, Fair enough, could be. Maybe let's vote. If you feel the top-down approach, so the first one is more intuitive, green sticker. If the bottom-up, the second one is more intuitive, say a red sticker. So green for top-down or red for bottom-up. Which one you prefer? Sort of mixed feelings from the responses. I think the original one, the top-down one, is much closer to the original description of the recursive algorithm, while the bottom-up approach is a different approach, but maybe to others more understandable. So I think there are mixed feelings, but fair enough. And we've looked at the trade-off between running time and memory and all of this. So some may prefer the one, some may prefer the other, and depending on how much memory, how much running time you have, you may have to pick the one or the other. So we have now finished recursion, and next we will apply recursion to sorting. We need recursion throughout this course. We can describe sorting very well in terms of recursion. We can also describe work on trees very interestingly in terms of recursion, because trees are recursive data structures. So we'll need recursion for various other topics in this course, sorting trees. We'll compare trees to maps and hash tables. We have a couple of selected topics in this course where we also need recursion. So recursion is a very helpful technique, and it allows us to describe certain problems in a very efficient way. But remember, recursion does not add any extra capabilities. It has its pros and cons, and converting sometimes to loops may be tricky, sometimes easier. But it's a very helpful tool. And also one note on this master theorem. So the master theorem is something really cool, but we see it's only applicable to problems that are described by such a pattern here. There is an extension or generalization of the master theorem, and that extension I have added to the course this year. However, it's not in the recursion chapter, but this year, so in a couple of weeks, we'll get to the selected topics and we'll discuss an algorithm that is called the median of medians. And in order to determine its running time complexity, we will see that it has a very sophisticated recurrence relation that we are unable to solve easily by hand, and it can't be used by the master theorem. So we use an extension of the master theorem or generalization, and that's called the Akra-Barsi theorem. And we'll see this Akra-Barsi theorem as a generalization of the master theorem in a few weeks. And that one we can use to determine the running time complexity of an algorithm called median of medians. So you see, you need this stuff again in this course. And in sorting, what we want to do is we'll compare different sorting algorithms. We will see bubble sort, selection sort, and insertion sort as very initial sorting algorithms. And then we'll see more efficient ones like merge sort and quicksort. We will also see how fast sorting can get um, at all. So what's the lowest complexity class for sorting? And we see bucket sort as a totally different approach to sorting in this course. And there was just another interesting question. if we can, for the top-down approach, if we can delete the memory if you don't use it for a while, yes, you can delete it. So you can just overwrite the memory with the initial settings. You have to manage this yourself, however. And if you have too many entries, your memory may just get too big. Maybe not for these integers, but if you do this for other objects that are maybe much larger, and when we used this LRU cache decorator in the last lecture, that cache is managed and it would, if it gets too big, it would kick out certain elements that have not been used for a while. So that's the idea of such a managed cache. But here we're not managing the cache on our own. Or here, sorry, we are managing the cache on our own. And so it just keeps growing and we would have to shrink it. And if it's not just integers, but larger objects, we could run out of memory at some point easily. And if you have a managed cache, this would get done for you. And caching is helpful, but caching can lead to new problems. Obviously, here we have a clear formula how to calculate Fibonacci numbers. But if it's a different process that is maybe more dynamic, um, we we may store values in a cache that are outdated. And so we would also have to clean the cache and make sure we don't read out these old, outdated entries any longer. And cache invalidation is, in fact, a major challenge in computer science, and I think a cause of a lot of computational errors that have made a lot of bugs. So if you have some way to manage your cache, that's helpful, but that would be a different class, probably not the introduction to algorithms and data structures. But here we have just built very easily something that does the same as the LRU decorator, but without managing the cache. So I hope this answered the question. So why is sorting so important? Sorting is probably one of the most important and best studied problems in computer science because oftentimes we need to store data in some order so we can efficiently search in it and retrieve or manipulate the data set. And you have seen this, for example, with the binary search algorithm. We can only use it once we have sorted the data sets, and then we can search it efficiently. If we don't have order in the data set, it won't work. Now, there are other algorithms that are more advanced. They also include sorting as a subroutine or as part of their work. So that's why sorting is super important in computer science, and that's why we need to study it. Plus, I've put it here in this section of the course so we can describe some of the sorting problems in terms of recursion. And once we have done this, we will see trees, which are another efficient approach to store and search data, and maps and hash tables are yet another approach. Um, so that's how all of these topics eventually fit together. And we can start before we look into these algorithms which always assume that we have n elements. If I don't fix n, or if I don't see n as a variable, I just say, how can we sort 2, 3, or 4 values? So we assume we just have a fixed number of values. We can try to implement this. And after that, we will actually see how we can do this for n many entries. So we can say, well, sort 2, we just sort 2 values, A and B. Oops, not in Python yet. So sort 2, A and B. And I can say if A is less than or equal to B, then I can return A and B in that order. So this is the cool thing about Python. I can return multiple objects at the same time. What this does is it's eventually just a tuple that I'm returning, a tuple with A and B, but I don't need to put these parentheses around. It's done automatically by Python. And if A is not less than or equal to B, I would just return them in the opposite order. Do you feel okay with this very simple sorting algorithm for two numbers? We can test it, sort two of 2 and 4, or 5 and 4, so seems to work. We can try to do this for three values. So we can do sort three, A, B, and C. And this one you will see is already a little bit more complex. So we can say, what if A is greater than B? Then we would need to change the order of A and B. And this again can be done very easily in Python. So in a lot of languages, you would do something like temp is A, and then A is B, and then B is the temporary value. So this is how you can flip two values in languages like Java or C++. But it turns out in some languages you can do this far easier, and so we can do in Python. So we can just say A and B, we just flip them because we assign B to A and A to B. Has any one of you done this with Python before? So you can assign values to multiple variables in one line. If you have done something like this, maybe just thumbs up or thumbs down. So it just saves us a little bit of code, and we use Python here because we can implement a lot of this just in a few lines of code. That's the reason why we use Python in this course. So if A is greater than B, we need to flip them. And so AB would be BA, so we just flip them. But we're not done yet because B could be greater than C. And sorry, no. If B is greater than C, then I also need to flip B and C. So BC will be C and B, because then we move the value in B that is greater than C into C. And now we have shuffled A and B and B and C potentially, but we need one more check because we may have had the smallest value in C before, and we have moved this into B, but now we still need to move it into A. So we may have to flip A and B again. So I again need to check if A is greater than B, and if so, AB will be BA, and I can return them in this order, A, B, and C. So we can test this, sort three, 5, 2, so 4, 5, 1, and this would be sorted 1, 4, 5. We can put in a 2 here, for example, as well. Then it's 1, 2, 4, and so forth. Are you still okay with this logic here? So thumbs up or thumbs down if this logic makes sense to you. There's the question, why do we have two times A and B? I said this before, so I'll be happy to iterate again. So it could happen that we have that, yeah, just for this example here, 4, 5, and 1. So I need to move the 1 into A. And here I check A and B. They are in order, but I flip B and C, and then I still need to check A and B again. That's why I have this check here twice, because I first need to bring A and B in order, then B and C, but then a smaller value may have been moved here and I need to check them again. Does this help for the explanation? So seems fine. So so the logic here seems to make sense, and we could even simplify our sort 3. So sort 3, A, B, and C, we can actually use divide and conquer, and we can sort A and B. So we can use our sort 2 from before, and we can sort A, B, and they will get come sorted back. We put them in A and B. B, C will be sorted. So we sort B and C, and then we again sort A and B. So we're just, instead of writing if and flip, we just use sort to, which we implemented before, and then we return A, B, and C. So we sort A and B, then B and C, and because something may be moved back from C into B, we still have to compare this to A. And our sort 3 also works here. Um, so we can see here in actually constant time, we can sort 2 or 3 numbers. We could also implement this for 4 numbers if we wish. So for a fixed number or a fixed number of values, this would be in constant time because it's not subject to the size of or to the number of values. It's just rules that we would execute, and it doesn't depend on the number of values because or it's not subject to n. While for doing this for 3 rather than 2, we need more constant operation. We don't have like a list input that is subject to n elements. Do you feel this approach is feasible? Say I want to implement now a sort 10. Do you think sort 10 is easy to implement or difficult? If so, for fixed 10 values that I want to sort. If you think implementing a sort 10 is straightforward, thumbs up. If you think it's challenging, maybe thumbs down. And maybe some more answers. So there's a majority for thinking it's complex. And in fact, that's true. This will become ever more complex because I need to use a lot of rules to ultimately implement this. And then it's still fixed in terms of the number of values. But in practice, I have data structures for which the size keeps varying and may become very big or very, very small, and my sort 10 would require exactly 10 values, not 9. So also that doesn't work very well. So the once we have implemented here sort 2, sort 3 in 2 variations, mm, actually this will not really scale building it this way. And then maybe I have an 11th value and I need to rethink that logic. So I need to do something different. And I need to come up now with sorting algorithms that work for n many values. So we need a more generic approach. And possibly the simplest approach is called a bubble sort. And a bubble sort is something that looks the following. I start with an initial data set that is unsorted potentially 5, 3, 8, 4, 6. And then I go through from the left and right and I compare the first to the second element and I swap them if necessary. And they get swapped because 3 is less than 5. So 3, 5. Then the bubble sort compares the second to the third entry and swaps them if necessary. Here it's not necessary because 5 is less than 8. Next, 8 and 4 are compared, as we see here, and they get swapped because 4 is less than 8. So we have 4, 8 here. And next, the last 2 entries get compared, 8 and 6, and they also get flipped. Doing this, I have not fully sorted the data set. However, I have brought in a little bit of order. And by doing this procedure from left to right, I am guaranteed that I have the largest value at the end. So the 8 is the largest value, and wherever it was, it will be now in the last position. So even if it was over here, in each comparison, I would move it over. And eventually, after I have gone through once the data set, the largest value is done. There's a question here if it could be that there is a smaller number in the middle and the sorting has to repeat. Yes, we see this also here. Like the 5 and 4 are not sorted. So I have done this one pass and I have brought in some order, but it's not necessarily fully sorted. All that is guaranteed is that the largest number, 8, is at the right, but the other ones are not necessarily fully sorted yet. So then the bubble sort says, I have to repeat this procedure, go through from left to right until ultimately there are no swaps anymore. And then I can abort. But I don't need to look into the last element anymore in the second iteration, because the last element is definitely already the largest one. So I have to repeat this procedure over and over, and at some point I would stop when there are no more swaps. How can we do this? We can implement this together, and you will see how the bubble sort would work. So the way I implement bubble sort here is a very, very simple bubble sort. You will see more coursework to implement this in a little bit better way. So it's just the simplest one possible. We can say, well, I have n many elements in, and this obviously not S, it's A. So we have n many elements, and I can go through all these n elements. So index from I to n, from 0 to n minus 1. But I need a second loop because what we said before is if I just use one loop, I go from left to right, I have maybe moved the largest element to the right, but I certainly may need to sort more because there's maybe still some unorder. So I actually need two loops. And so I could say I have a second loop with index j, and j goes, we could say, to n minus 1 initially, but we'll see we can do better because we said after one pass, the rightmost element is the largest one. But if I do a second pass through the data set, then the last two elements are sorted. So what I would say here is J does not need to run to n minus 1. Actually, it can run to n minus I minus 1 because as the outer loop has passed a second time, then the rightmost two elements are sorted and I don't need to look at them any longer. So I have a loop within a loop, and now what I can check is if element aj is greater than element aj plus 1, that means an element, the left element is greater than the right element, then I need to flip them. And we've seen before how we can flip in one line, but because we have these indexes, this may look confusing at some point. So I'm introducing here my helper variable, and I say temp is the value in j, and value in j is now overwritten with the value in j plus 1, and j plus 1, that value will be the temp. We could do it in one line, but with these indexes, it may confuse some people. And now I can create a data set, which I say it's 9, 2, 1, 4, and 5. And I am passing the reference to A to bubble sort. So I'm not returning anything from this bubble sort, but I'm manipulating A because A is a reference to my list. And what I see is it's eventually sorted. 1, 2, 4, 5, 9. So, bubble sort is a very simple sorting algorithm. Do you have any guess, maybe without looking in the slides, what could be the worst case complexity of this bubble sort? O of what? If you have a suggestion, what's the worst case O complexity, send it to the chat. We have one guess here, maybe some more. One student guesses it's O of n squared, and n squared is correctly. You can actually prove this quite easy because you would wonder how often could this line be executed in the worst case. And I runs from 0 to n minus 1 and j from 0 to n minus I minus 1. And you will see that this line in the worst case is run O of n squared many times. We've seen this technique before, how to look into multiple loops and then infer how often in the worst case a line gets executed. And so in fact, this is O of n squared in the worst case. And one student asked me every year the same question, so I'm already prepared. Um, One student asked, why do we put n minus I minus 1 and not something different? So I've shown this here for a single pass. A single pass through the data set leads to that the rightmost element is the largest element possible, because in the worst case, I move the largest element from left to right. That one in green is sorted. The other ones are not necessarily sorted. So I could put in here an n minus 1 because I don't need to look into the last one anymore. In fact, the way I use these indexes, it's aj and j plus 1. So if I put in n here, then I would, with j plus 1, try to access an index that does actually not exist. Now, why is it minus I minus 1? Because if I run this a second time, then this one here will be sorted. So the 6 would be the second largest element, and this one would be the element to the left of the largest one after another pass. And after a third pass, the 5 would be where we have the 4 now. And then I don't need to look at these last elements anymore, and I always can skip one more for one more pass through the data set. And that's why I say n minus I minus 1, because I gets incremented when I have done one full pass through the data set with the inner loop. Hope this answered your question. Maybe just confirm if this helped. Yeah, so the complexity here is, in a worst case, it's O of n squared. The way we implemented this algorithm, it would even take O of n squared in the best case, because there's no criteria to abort anything. And in fact, this is something you can check in the coursework. You can implement this algorithm here a little bit better, that in the best case, it only takes O of n. In the best case would be you have a data set that is sorted already. That would be the best case. But with bubble sort, what would happen is we would really try to sort the whole data set again. So the best case is O of n squared. If you improve this implementation a little bit, at least for the best case, it will be O of n. And this is one of the coursework problems, because we have this coursework here, and problem 11.1, it's your task to rethink this bubble sort implementation. So we have a best case running time complexity of O of n, and there is a small hint of how to improve this. But the worst case will not change. And average case is O of n squared as well. And the space complexity is O of 1. So space complexity here means, well, we have an index, we have this n, we have an index here, we have a temp, but then the space is not subject to n, because here we have a so-called iterator, but that's something we will see in a few weeks what an iterator does exactly. But the size of that or the space of this is constant. So we say an algorithm for which the space is constant or not subject to n, this is an in-place algorithm. So in place means constant space. And this algorithm is stable. Um, and here, you all who are listening, either the live lecture or the recording, sometimes I ask in the exam, what is a stable sorting algorithm? And most of the answers I get, or maybe not most, but a lot of the answers I get is weird stuff that I have never heard before. Like students claim the algorithm sorts correctly, but sorting correctly, I guess that's what we assume anyway. So I will now explain what a stable sorting algorithm is, because every year that's somehow a big problem in the exam, while it's actually a very simple concept. Now, imagine I have a data set like here, and I have two duplicate values. Imagine I have a 5 here and I have a 5 over here. So that could be possible also with my algorithm that I have um, implemented. We could put in duplicate values. And the question is, how do these duplicate values get treated when sorting? So I have a 5 here and say a 5 at the end. And when I sort the data set, I want to make sure that the order of these two fives has been preserved so that the first 5 will later be the first 5 in the sorted data set, and the second 5 would be the, for example, here, the next 5, so that we don't change the order of equal values. Why does this matter? You probably don't see that this would matter for integers. And for integers, it's probably doesn't matter much. But you could have totally different values, different objects in your data set, and you may wish to sort them in based on multiple criteria. First on one criteria, then on another criteria. And when you have two entries that have the same value in that criteria, and you sort them based on a new criteria, you don't want to change their respective order. That's the idea of stable sorting algorithms. So stable sorting algorithms, they would sort repeated algorithms in the same order as they appear in the input. And the bubble sort we implemented is certainly stable because it only compares left to right and only flips them if the right one is greater than the left one. So bubble sort is stable, but other sorting algorithms are unstable. And maybe you have seen this before when you use like a tool like Excel. You can sort um, you can sort your rows based on multiple columns. First on the one column, then on the other column. And there you would really expect that you have a stable sorting. Otherwise, you sort on one criteria and you have two entries that have the same value and you have an order between them. And then you would reorder them based on another criteria. And this would probably look quite confusing. So for that kind of stuff, you would need a stable sorting algorithm. There's a visualization here of what stable and unstable could mean. You can look this up on your own, but I will show you a concrete example where we have multiple criteria to see why this is helpful. So I have this sentence here, and maybe you're now sitting in front of your computer, all try to say this. I know it's a tongue twist, like it's hard to read out for some people, so I'm trying my best without having practiced this. So last time I read this sentence was when I taught this course last year. So it's like, how much wood would woodchuck chuck if woodchuck could chuck wood? You can try, you can say this. It's like in German, Fischers, Fritze, I know. I guess that the ones who speak German know that example. And I take this input string, and what I'm doing now is I'm doing a word count. And my word count would be I'm counting the words. So how appears once, much appears once, but would appears here and there, so twice. Would, so something would happen appears once. Woodchuck appears twice here and there. Chuck appears twice. If appears once. And could appears once. So we have done a word count. So the sorting has not happened yet. The sorting will come next. And what I'm doing now is I'm doing a first sorting based on the word, so a lexicographic sorting. So I'm sorting this. So these are tuples, and the tuples have two entries, a word and a count. And now I want to sort these tuples based on the word. So Chuck comes first, then could, how, if, much, woodchuck, would. So we just sort this alphabetically. Technically speaking, we're doing a lexicographic sorting, but you can just say an alphabetic sorting here in this example. But now I have sorted the tuples based on the word, and now I want to sort these tuples again based on their number. But I want to take this sorting and sort based on the number. So what I want is, say, I want number 2 to appear first, and with a stable sorting algorithm, Chuck would appear first because of all the ones that have 2, Chuck would appear first, then would, and then woodchuck. And that's exactly what I have done over here in the last column. Chuck, would, woodchuck with 2, and then all the words with count 1. And I also would keep them, the ones with order 1, as I have, or with count 1, I would keep them as in the order of the first pass. Could, how, if, much, would. Could, how, much, if. Sorry, could, how, if, much, would. Now, so this would be the right order with a stable sorting algorithm, because the first pass, I did this alphabetic search, and then I take that result and sort it with a stable algorithm based on the count. And I would say it's a descending then, so all the 2s and the 1s, but the 2s would be in the same order as before, and the 1s would be in the same order as before. And if I take an unstable algorithm, yes, I would get first all the entries with value 2, and then all the entries with value 1. But within the group of 1s and within the groups of 2, I may have a different order, and I'm not preserving the order from the first pass. And that would be an unstable sorting algorithm. Maybe just confirm if you got that difference between a stable and an unstable one. I see a thumbs up. Maybe some more ones would be great. And I also have a definition here. And we have this example down here as well. So if I have this data set and I sort it, I would sort this into 3, 5, 8, 8, 9, but the order of these two 8s does not change, while an unstable one, I have the right result, but I have flipped these two 8s, and that would be an unstable sorting, which just for integers doesn't make much of a difference, but it appears for objects that have multiple values, and then I sort based on one criteria or criterion, then on the next criterion, and so forth. So that's the difference between stable and unstable sorting. Now, so bubble sort is a very simple algorithm. Can be implemented very easy. The problem is the worst case complexity is O of n squared. And that's super slow. Imagine you have millions of elements, then this will not finish anytime soon. Even though you can implement it very easy. There are, however, a few use cases when a bubble sort is actually useful, believe it or not, but that's something we're discussing at the end of this chapter. There are two other relatively simple sorting algorithms, and these two algorithms, they get a lot of attention in the literature for some reason. And they are called selection sort and insertion sort. They are two other relatively simple sorting algorithms, and they are both quite inefficient, by the way. And a lot of algorithms courses, so the one that I took when I was a first year student or other courses that I see, they somehow discuss in great detail the selection sort and insertion sort. This can be done, or we actually focus on real algorithms that are relevant to real world problems. That's why I think with the bubble sort, having discussed one simple sorting algorithm, that's enough. And we'll go to the more advanced ones that are also more efficient. But if you're curious about how selection sort and insertion sort work, uh, it's in the Goodrich book. There's plenty of advice online. What you would see is the selection sort has a worst case complexity of O of n squared. Best and average is also O of n squared. The space complexity is O of 1, and the selection sort is unstable. The insertion sort is at least stable and has a best case complexity of O of n, but again, the worst case of O of n squared, plus the average one here is O of n squared. So not very helpful for a lot of problems. That's why 3 slides about them should be sufficient. If you want to study them on your own, go ahead, but they will not play any major role in this course. We will now look at two very efficient sorting algorithms instead, and they are used in the real world and they come with real consequences. And so I think we better study them. One is called the merge sort. So the merge sort is a divide and conquer algorithm, and it works bottom up. You remember the concept of bottom up and top down that we introduced at the end of the recursion chapter today in dynamic programming. And so we reuse this terminology for sorting. Bottom up, so merge sort works bottom up. It's an efficient divide and conquer algorithm. Later we will see quicksort, which is a top-down algorithm that is efficient and does divide and conquer. It's a totally different approach, and we'll compare them. How does the merge sort work? So I have an unsorted list, and I divide it into n sublists, and each sublist contains one element. So just one element. And then I repeatedly merge these sublists to produce new sorted sublists. So I take, for example, 2 entries that are next to each other, and I merge them into a list of 2 entries, but that merged list is sorted. Then I take the next 2 entries and merge them together, and the next 2, and later I take these small lists of 2 entries and I merge them, so 2 and 2 into 4. So each time I take a sorted sublist, and starting with one element, I have a sorted sublist, and increasingly merge larger sublists that are already sorted together into sorted sublists. So, and eventually I do this bottom up, starting with single elements and increasingly have larger sorted lists. And then I'm done when I have ultimately sorted all of this together or merged all of this together, and I will have a sorted list. I will show you the concept that this algorithm or how this algorithm works. So imagine I have my data set, which is 85, 24, 63, 45, 17, 31, 96, and 50. I would split it into a left sublist and later the right sublist. And this left sublist is still too big, so I still need to merge it into smaller sublists, which is then 85 and 24. I still have the 63 and 45, which will come later. And the 85 and 24 will be split into single elements, 85 and 24, because I then have the 85 here and the 24 there. So I have single elements. Then I can start merging them together because I have the 85 and the 24, and I can bring them in order because I just compared them, 24 and 85. I keep doing the same for the 36 and 45. So I split 36 and 45 again into single elements, which is 63 and 45. And then I merge them together, and then they are sorted 45 and 63. Now I have this sublist from before, 24 and 85, which is sorted, and 45 and 63 are sorted. So I can just merge them together, that I first pick the entry here, 24, 45, 63, 85. So the challenge here is splitting the data set into ever smaller subsets and then having single elements and then put them into the right order. I have a list of two, then another list of two, and then I merge these lists together until I have a larger list, which I have done here. So that 24, 45, 63, 85 is done. I still have the other right sublist, 17, 31, 96, 50. This would still need to be splitted and merged. And when we do this, so we assume we do the same procedure, we will have 17, 31, 50, and 96. And now we need to merge this sorted one and this sorted one together. And I will get 17, 24, 31, 45, 50, 63, 85, 96. Do you feel you got the concept of how this may work? We split and then we start merging single elements and we merge them. Then we have something sorted and then we merge bigger sorted stuff. Maybe just confirm if you sort of got the idea of what this algorithm is supposed to do. How it can be implemented is obviously a different question, but I see so far that you look positive. The only thing is we should study a bit better is how can this merging be done? So merging always works on sorted sublists. And here I have two sublists that I want to merge, S1 and S2. And what we have here in white is already merged together. So the result is S, and S will be the result of merging S1 and S5. So we take the 2, then the 3, the 5, the 8, the 9. They are already in. And now I have a pointer I pointing to index 3, which is the 11, the next element to be assessed in S1. And the next pointer j has index 2, which is value 10. And now I want to take the next element. So I need to compare this value to this value and take the smaller one and then move the respective index by 1. And the smaller one is 10. So I would put the 10 in here and move this index j from 2 to 3. So it points to the 18. Next, I would take the 11, then the 12, 14, 15, and so forth, and then the rest. So this is the idea of merging. Merging is a subroutine used in merge sort because the merge sort, what it needs to do is the splitting, and then I need to merge it together using this merge function. What I will show you is how to implement the merge sort. You're wondering probably how can I implement the merging? This is your coursework. So the merging can be implemented actually fairly easy. It's just a few lines of code. So merging is problem 11.2 in the coursework. So you merge S1 and S2 into S. I don't know, I've just copied it here and it's probably some less than around 10 lines of code. Just implementing this one here, you have an index I pointing to S1, an index J pointing to S2, and you write in S at index I plus J. And the important thing is you don't drop any values from S1, you don't drop any values from S2, and S2, as we build our merge sort now, S will already have the right size. So you don't need to do any append or resize. All you do is you write into index I plus J. So that's your coursework. It's actually not that difficult, and there are also some, obviously, you can look into the Goodrich book, how the Goodrich book proposes this. So you read from S1 and S2, or you write into S. You don't remove anything from S1 or S2, and you don't need to update the size of S. We would assume the way we build now merge sort that S has the right size already. So that's important. So how can I implement my merge sort? And that's what I will show you now. So we implement the merge sort and we manipulate S. So we pass a list to S and we don't return anything. We write into S. And if S has a certain number of elements, we don't need to change the size of S anymore. We wonder how many elements are in S. And if n is less than 2, so if I have 0 or 1 elements, I'm done. Then S is already sorted, because if S is empty, there's nothing to sort. And if there is 1 element in it, I'm done also. Now, I need to split S into S1 and S2. And what I typically would do is I would split S1 and S2 by splitting S into half. So what I can say is I need a middle index, so n divided by 2, and I want an integer division. And then S1 would be all values up to mid, where mid is excluded, so from 0 to mid, but I can just write it this way in Python. And S2 would be all values starting from mid, where mid is included. I could put in an n here as well, but I can just leave it off, and then the last element, it will run up to the last element. So I have just split S into S1 and S2. And I need to do this now recursively again for S1. Because S1 is now a certain number of elements, half the elements of S. But I need to keep doing this until there's just a single element left. So until ultimately something returns. So I need to split my S1 recursively into smaller subsets. Once I'm done with that, so this was the left side of that recursion tree that I had shown you. I'm doing this for S2. And what I get back is S1 is sorted and S2 is sorted. And then I need to merge my sorted S1 and sorted S2 into S. And this is happening recursively until there are just single elements left, or single elements in a list. And these lists with single elements would be merged here together into a bigger S. And S is that reference that we are passing to the merge sort when we recursively call it. Are you surprised that the merge sort can be implemented that easy just with like 10 lines of code, approximately 2, 4, 6, 8, 10? If you feel this is surprising, well, this is the power of recursion, because we have looked at the visualization of merge sort, and it turns out I can just use divide and conquer, because I keep breaking S1 into smaller ones, S2 into smaller ones, and later I just merge it together. What, what is not working for you now is if you code this, you still need to code merge, but this was part of the coursework, or you look it up in the book. We can have a sample data set as before, like 8, 20, -4, something like this. And I can run merge sort on this, and you see my A got sorted. Yeah, merge sort is super efficient, and you are probably wondering why. I'll show you this now. So the slides show this merge sort implementation. The slides don't show the merging. That's your coursework 11.2. And so what is the running time complexity of merge sort? The good thing is all the worst case, best case, and average case is n log n. So n log n is way better than n squared. And we always optimize for the worst case. So n log n scales extremely well, even to trillions of elements. While if n squared, this will not scale to trillions of elements. So when we started complexity theory a month ago, I told you complexity is super important and we'll need it throughout the course. The space complexity of merge sort would be O of n because what I'm creating here are these new S1 and S2, which are copies of S. And in fact, it turns out there are probably even better ways to implement this merge sort in terms of its memory footprint. But typical reference implementations of merge sort would be O of n space complexity. So it needs way more space than our bubble sort, because bubble sort was O of one space, but n squared. But a good bubble sort would have a best case of O of n. So if you have a data set that is sorted already, the bubble sort would work slightly better and would not need all that memory. So you see the bubble sort still has some pros. And merge sort is stable. And now we said merge sort is a bottom-up divide and conquer algorithm, and it's super efficient, by the way. Now we can look into its competitor, quicksort. Quicksort also claims to be efficient. It's also a divide and conquer algorithm, but it works top down. So it works in a totally different order or a different way than the merge sort. And it's called quicksort because there's a claim that this is actually quicker or very quick, but it's more complex. I also want to inform you about one thing. You're wondering, where does this complexity come from? Why is it O of n log n? Remember, I take the data set that has n many entries, I split it into two data sets that are half, so n half, but I have these two recursions, so 2 times n half, and then I have this combining or merging, which is n, or O of n, because n many elements need to be merged. And this is the recurrence relation we studied today through the master theorem. We studied it in the last lecture, and I said there was this general algorithm pattern where t of n is 2 times t of n half plus n. Do you remember when we solved this? Maybe thumbs up or thumbs down if you remember when we solved t of n is 2 times t of n half plus n. And I said that pattern is important. So I see many people remember, and this pattern, or the pattern, that's exactly what we are doing here. 2 times t of n half plus n. So this behavior of merge sort, you could pose this recurrence relation that we have seen and solve it. It's n log n, at least here for the worst case, but also in the best case, we split it. And in the average case, we also split it. And also a sorted data set would be splitted. So the behavior is exactly the same for worst, best, and average. Also for a data set that is sorted already, we have exactly the same behavior. So that's merge sort. And now you know why the complexity is n log n. And now you know why we did recurrence relations before doing merge sort and why we did the master theorem before. So you can pose the recurrence relation or come up with the recurrence relation and you know how to solve it. So in my agenda in this course, that's the big picture. We first do recursion and then the sorting, because then you have all the tools to determine this fairly easy. Unfortunately, this quicksort is more complex. And it's called quicksort because it has a big claim, and the claim is it runs actually super quick. And we will see now how quick and if that's always the case. Um, just comparing something. Yeah. So the quicksort here works in a different way. And what it does is the following. It selects a pivot element, so one element from the list, and one element, we just say one element from that whole list that we want to sort, and we want to partition all the other elements into two sublists. So we take one random element from our list and say we have one sublist with all the elements that are smaller than that pivot element, and the other list are all the values that are greater than the pivot. So that's the idea of a pivot. And then we have these two sublists, one with all the elements smaller than the pivot, and one with all the elements greater than the pivot. And we keep doing that again. So we do this for the left sublist and again for the right sublist. So we keep sorting and sorting by using this pivot. The pivot does not sort directly, but we take everything less than the pivot in one list and everything greater than the pivot into a different list. And we can visualize this. So quicksort looks like this. I have a data set 85, 24, 63, 45, 17, 31, 96, 50. And you may see that one element is here in bold. This is the 50. I think they would have, so there's the figure is from the book, but ideally they could have just underlined it or so, that would be more visible. And this is the pivot. So here we just arbitrarily pick the rightmost element as the pivot. We'll later see if this is a smart choice or not. We could also pick the leftmost element or some other one, but we'll see this in a moment. And then the entries that are smaller than the pivot is 24, 45, 17, 31. And greater than the pivot are 85, 63, and 96. So we have a left sublist and a right sublist. And in here, we again always pick the rightmost element as the pivot. So 24 is smaller than the pivot and 17, and the 45 is greater than the pivot. And for this sublist, we do the same again, 24 and 17. 17 is the pivot and 24 is greater than the pivot. For this sublist, we're doing the same. 85 and 63 are less than 96, so there's only a left sublist. And 63 is the pivot, so 85 is greater than the pivot. Maybe I'll just confirm whether you got this idea of a pivot, of how we select this. Looks fine. Now we can try to not merge, but a consequence of the pivot would be the following. So we can say we now plug all of this together. And for this sublist here, we can say, well, once we are done, once we just have, for example, single elements left, we take the left element, so what is smaller than 17, which was empty, there was nothing. Then we take the pivot, and then we take the 24. And so we could then up here say, well, the 17 and 24 is left of the pivot, that got sorted, then the pivot, and then the 45. And so over here, we bring in order 63, 85, 96. And for the whole list, we take the left list, 17, 24, 31, then the pivot, and then the right sublist that also got sorted by splitting based on the pivot. And that's exactly what we want to implement now. And there are a lot of ways how we can implement quicksort, and we still need to see the claim whether this is actually quick. So we have quicksort for a sequence S. And again, we need to check if the length is less than or equal to 1. And if so, we just... So this time we built the algorithm in a way that we don't change S, but we return something. This will make this implementation slightly easier. So in this implementation, we actually return a sorted set or sorted list. And here we have S, and if S has 0 or 1 elements, we just return it. And now we need a left list, we need a right list, and we need a pivot. But in my implementations, or in the implementation I had shown you in the slides, we always took the rightmost element. Say this time in my pivot, I take always the leftmost element. And now all I want to do is I want to split based on, is an element greater than the pivot or less than the pivot? So I go through my elements in S, and if my element is greater than, or say greater than or equal to the pivot, because there may be duplicate elements, then I append this to element, to right, I append element to right, because element is greater than or equal to the pivot. Otherwise, I append the element to the left. Are you all okay up to here? That this is how I could use the pivot to split into left and right. And I see some good responses. And now I'm doing exactly the same as before with the left sublist. I can recursively split the left again into left and right. And eventually the quicksort will still do a few steps that we will see. And what will come back from quicksort at the very end in this recursive call is a sorted list left. So I'm doing the same with recursively with right, and I am getting something sorted back from right. And then I just need to glue them together and I'm done. There is one minor change I need to make that this works, because you see I go through all the elements in S and I check if an element is greater than or equal to the pivot. And the pivot here is element 0, the first element. So the first element would actually say, yes, the first element is equal to the pivot, so it will be added to right. So I would here just take all the elements as of index 1. So index 0 is exactly that pivot, so I'm ignoring that in right, because I don't need to pass that one into the recursion, because the first element in right, so index 0, is exactly the pivot because of this constraint. Now I'm getting from quicksort a sorted left list, a sorted right list together or back. So I can just concatenate the lists left plus right, but I also need to concatenate the pivot. But pivot is a single element and I can't concatenate lists in single elements. You've seen this before with our graph search. So I can put pivot into a list, single list with a single element. I concatenate the left list with the pivot with the right list. And I have sorted my data set. And again, with recursion, I can describe this so easy because all I'm doing is keep splitting the left list until I just have 0 or 1 elements left. I keep doing this for right, and later I just put this left and right element together with the pivot. I have it sorted, and I keep when I complete the recursions, I glue all of this together. Before I had a data set, which was this one here. So let's put it in and see what it returns. So quicksort of A also returns a sorted set. So this time returning, we don't manipulate A, but we return something. So quicksort has a very interesting name and it claims it's quick. And when we look into, say, this figure, I'm just opening it. So we've just implemented this. This is a very simple quicksort, and it's not very efficient from terms of the memory, but it's at least probably one of the simplest ways how we can implement quicksort. What we notice here is something quite interesting. So this was the visualization, and here we always pick the rightmost element as the pivot. We pick the leftmost element, and somehow we see these sublists, they are about the same size. Do you think this will always happen, that the left and right list are more or less the same size? Or could some other extreme happen? If you have a suggestion, maybe turn on your mic, because I also want to discuss with you this, or send to the chat what could happen. Or at least send some reaction if you think you see what could be happening, or maybe some red reaction if you don't see what could be happening with our quicksort. So one person sent something positive. Do you want to tell us what you noticed with this approach? What could be happening? Do we always have two sublists that are more or less the same size, or could something go wrong? I'll wait for your response. One person guesses that all the elements could be in a single list. Yes, all elements, say, except the pivot. Say if say we picked 96 as the pivot, say 96 was the rightmost element. It's the largest element, so all the other elements would go into the left list. And if that happens over and over again, and we never really get to split the list into two equally large sublists, then this will become super inefficient, right? I want to see some guesses from you what you think the complexity could be if we don't split this well. Say we always just split into one large sublist. How deep this tree would be and how much work this could take. So you can send some guesses of the O here to the chat. What you think the O complexity could be. So one student says, if we always pick the rightmost element and it's the biggest number, all the other elements are smaller and they would go into the left list. So I want to see if you can, if you want to guess a little bit, say, please guess in the chat what you think the worst case complexity could be. So worst case is we are unable to really split. I want to see what you think the O complexity could be. And meanwhile, and just guess what you think this complexity would be. O of what? And I'll show you this now in parallel on my iPad. Um, it would be cool if, because nothing can go really wrong with your guess. So I want to know if I have, so quicksort, n elements, bad pivot, it's O of what? Let's see. Say bad pivot is all the elements going to the left sublist except the pivot, or all going to the right sublist except the pivot. And I have to run a lot of recursive calls. What do you think this O of n could be in the worst case? So worst case. I want to see if anyone can guess it. O of what? So one student guesses, so we got some guesses here. One guesses O of n to the power of n, O of n squared. Um, Multiple people guessed O of n squared, and it is in fact O of n squared. Why? So it's fortunately not O of n, but O of n, sorry, not O of n to the power of n. It's O of n squared because I may need a recursion level of n. So I may have to do, or like n minus 1 recursive calls to keep breaking this long list into smaller sublists, because each time I can only really remove the pivot and nothing else, because all the elements go into one of the sublists. And moving this to the sublist would be O of n, and doing this n many times, or say n minus 1 times for the recursion, I would be at O of n squared. Maybe just confirm whether you got that initial idea why it could be O of n squared, what I just explained, if that made sense. Because moving into left and right is O of n time, and I may have to do this like n minus 1 many times in the worst case. So the recursion tree is very, very deep. But this was just some of my thoughts. We could think about the recurrence relation. So it's really the worst case now. The recurrence relation could then be something like T of n is T of n minus 1 plus n, and T of 1 is 1. Because I need n much time to move all of this around, and in fact, all I have removed was just one element because um, because I wasn't really able to take advantage of this splitting here. So this could be a recurrence relation that you can think about and try to solve it. We had solved a different one before. So note, well, we had not solved it together, I think, but it was on page 233 of my slides. We saw that if T of n is T of n minus 1 plus 1, then T of 1 is 1, T of n is O of n. So this was something we had put in the slide as a reference, but here this is a 1. And that one would come, for example, from a regular sequential search. Then something like this would be O of n. But here, for our worst case quicksort, we don't have a 1 there, we have an n. So um, if you solve this recurrence relation, you will see it's O of n squared. And this one, you have to solve manually. The master theorem will not help you because you subtract one, you don't divide n. So um, page 233 in the slides, and I'll just show you this. This was this slide here. Um, where I had this recurrence relation, and this would be a sequential sorting, but then it was plus one, and here would be plus n because we need to move all these elements into left and right. Um, so this could be some thoughts why the quicksort can go really wrong for if the pivot is picked badly. So we got some questions here. Um, One student here asked, should we always expect the lists to only contain numbers, or should there be a check if strings are part of the list? You don't need to expect numbers, but we are working with comparison-based search because we always say something is greater than the other. So it doesn't need to be numbers, but it needs to be objects that you can somehow relate to each other or compare in terms of some criterion. You could maybe calculate some score from a string or something else, but all we are doing here is comparison-based sorting. And the string, yes, you can also bring order in strings because we do alphabetic sorting then. We've seen this before when we looked at stable sorting. So this lexicographic sorting, that could be then one criterion. But to keep it simple, we only look into numbers now. But whatever data you have and you can bring some order in or some comparison, that would be fine. Hope this answered the question well. So now we've implemented this very simple quicksort, and the problem with quicksort is the worst case is O of n squared. So what is actually the worst case? The worst case is picking your pivot either in the very left or either the very right, and you put in a list that is sorted already. Because if it's sorted already and you pick the left or the rightmost element as the pivot, this behavior will occur. And it will still run super bad if, and also in that range, if your data set is almost sorted. So if it's almost sorted or nearly sorted, again, this pivoting with left or right will not really help. Do you have any suggestions how we could pick a pivot? If you have suggestions of how we could pick a better pivot, what you think, send this to the chat, and we'll compare your strategies. While I wait for you, I'll already say a few words. Quicksort has a best case and average case complexity of O of n log n, because in the best case or in the average case, we would split with the pivot into approximately two lists that are the same size, and then this recurrence relation from merge sort would apply, and it would be O of n log n. And at least the initial implementation of quicksort is unstable. That's a problem. A good quicksort would have a space complexity, for example, of O of log n, but that's much better than our simple implementation. So this one here is actually quite inefficient. One student suggests we could use medians to find better pivots. Yes, that's a strategy that is but often not too common in sorting algorithms. Using the median for better pivots is a strategy we would often use in so-called selection algorithms. So a selection algorithm would mean not sorting, but say find the third smallest or fifth biggest. That would be a selection algorithm. In there, such a median strategy is quite common. Could be used here for sorting as well. We will see this for selection algorithms in selected topics. But you can pick a different strategy, and a different strategy could be picking pivots randomly. So not the middle, not the left, not the right, but randomly. And this is addressed in problem 11.3 of the coursework. However, picking pivots randomly, it's still worst case is O of n squared, yet it is super unlikely. And there is a reference here that you're welcome to read and think about this in problem 11.3. The worst case would still be O of n squared, yet it's super unlikely because you could just have bad luck each time with your random pick. Yet this is super unlikely. So problem 11.3 addresses this, and this would be a randomized quicksort where we pick the pivot randomly. But still, worst case is O of n squared. So why is quicksort called quicksort? In practice, still for most real-world problems, quicksort is typically the fastest sorting algorithm that we have available for a lot of settings, for the majority of settings. And this worst case, especially with a randomized strategy, is super unlikely. And in practice, quicksort runs faster than merge sort, even though say so average case is O of n log n, and in merge sort it's O of n log n. In practice, a well-tuned quicksort would outperform a well-tuned merge sort. There have been a lot of studies about that. One problem with quicksort is that it's unstable, but here comes an addition. There are a lot of variations of quicksort and merge sort. So we said our quicksort is top down and the merge sort is bottom up. There are variations of that as well, like top down quicksort, bottom up quicksort. Of same for the merge sort. There are a lot of variations. There are quicksorts that are stable. Yet with that approach we have picked in quicksort, the worst case is O of n squared, and with a randomized one, it's still O of n squared, yet less likely. There is an algorithm called heap sort that is also interesting. It uses a heap, so a sorted or a special data structure that has a certain sorting criterion. And its worst, best, and average case is O of n log n. And heap sort is O of one memory. So this sounds really cool. Worst, best, and average O of n log n, O of one memory. But in practice, the heap sort is slower, at least to some extent, than a well-tuned quicksort or merge sort. So the heap sort is largely a theoretical thing. In practice, it's not used too much, even though it's O of one memory. And worst, best, and average is O of n log n. It performs in practice slower than a well-tuned quicksort or merge sort. There is also a BOGO sort. A BOGO sort is obviously a joke because BOGO sort would mean we randomly shuffle a data set, and if it's sorted after randomly shuffling, we would complete. If it's not random, if it's not sorted after randomly shuffling, we would shuffle again, and we would only terminate once the data set is sorted. So sorting by accident. That's obviously a joke. It doesn't make any sense. When we see quantum computers, we may talk about the quantum BOGO sort, but that's again sort of a joke. But if you hear about BOGO sort, it means random shuffling. So this is what you need to bear in mind. There are a lot of variations of quicksort, merge sort. This coursework here will probably help you a lot to understand this better. Yet there are a few more things about sorting I want to discuss with you in today's lecture. Um, I added this. I saw this a while back on the internet, so I think I added it this year. This is a joke, obviously. Someone proposes a sorting algorithm called Stalin sort, and it's a single pass O of n algorithm, and you iterate through the list of elements and you check if they are in order. If an element is out of order, it will be deleted or eliminated, and at the end you have a sorted list. So we'll just go through and see if the next element is greater than or equal to the previous one. If that's not the case, if it's less, it would get eliminated. So it's obviously referring to the war crimes committed by Stalin. Stalin sort. I don't know who came up with this, but I saw this post a while back. Hope you find this at least funny for quick entertainment here at the end of the course. Or we still got maybe 10 or 15 minutes today. What I recently saw on YouTube is there are a lot of videos about visualizations of sorting algorithms, and there's a new series I came across recently with all the sort of same visualization. There are some useful algorithms, some made up algorithms. So if you see them on YouTube, uh, do watch them. So Stalin sword, you can try to implement this too. Um, Never thought about putting this in the exam, but well, we could actually at some point. It's not a promise it would appear in the exam, but would be sort of funny. But you can implement this very easy then. So you know how to implement such stuff. And what is interesting here, so this was at the time when I was in at the end of high school, when Obama was running for president. So in the early stages of his campaign, he visited Google, the headquarters of Google in Silicon Valley, and he was in the Senate at that time, and he was running. And this is Eric Schmidt. He was chairman of Google at that time, and they interviewed Obama about different political stuff, but they also interviewed him about computer science. And Eric Schmidt asked Obama what he thinks would be the most effective or most efficient sorting algorithm. And I guess obviously Obama was sort of prepared, but you can watch the video and see what his response was at the time he was running for president. Now we've seen quicksort, O of n log n, merge sort, O of n log n, heap sort, O of n log n. Now the big question comes, can we do faster than O of n log n? And it turns out if we have comparison-based sorting, so all the stuff we looked at so far, we compare entries with each other, that's omega of n log n for the worst case. So obviously best case can be O of n because if it's sorted, we just stop. But the worst case means the worst case input, what we optimize for is an omega n log n. So we can't do better in the worst case than n log n. This has been mathematically proven many decades ago. But some people interpret this wrong, and some people claim sorting could not be faster than n log n. But that's wrong. It's comparison-based sorting. So all the stuff we've done so far is comparison-based. But if you have some other approach that is maybe not based on comparisons, maybe that one could be done faster. And so there is a whole different family of sorting algorithms, for example, called bucket sort or radix sort. And what they do is a totally different approach to sorting. And they don't use comparisons, but rather something else. So bucket sort, you need to imagine that we take our data set and we distribute the elements of our list into a number of buckets. Now we have buckets and we split this. And it can be shown that the running time is O of n under very specific circumstances. For example, I have n entries, and so I have k buckets. and I distribute these n elements into my k buckets, and I assume a uniformly distributed input, then I can do the sorting in O of n under these specific circumstances. But this may require a lot of memory. And sometimes the literature um, distinguishes between radix sort and bucket sort, but I think more or less this is pretty much the same, or at least to most people. And there are again a lot of variations of this approach. But the bucket sort does not work very well, say, if you want to sort floating point numbers or other types of data that you cannot easily map to a small number of digits. So this may work under very specific circumstances for integers well, but not for floating points or other objects. And it still may require a lot of memory that this runs in O of n. Um, so probably applications to real world problems are rare. They may exist though. I found a very interesting blog post from some 10 years ago where someone wrote or claims he wrote a faster sorting algorithm. He didn't really write a faster sorting algorithm in general, but rather under some certain assumptions that he made. And it's sort of a variation of radix sort or bucket sort. And other people have been writing about this too. But typically this, or it usually always addresses some special cases. So better than n log n, yeah, possible, but difficult and with limited applicability. So what most people do is obviously comparison-based sorting. Sometimes there may obviously be exceptions for the exact kind of tasks. Next question is, we've seen bubble sort, and we saw its worst case is O of n squared, and really O of n squared, not like with quicksort, that this randomized quicksort would be very, very exceptionally O of n squared, but rather the bubble sort is really O of n squared. So it may look like it's completely useless, but it turns out that bubble sort has some applications. And there was a very interesting discussion on Quora quite a few years ago. And there was a person, he argued why bubble sort can be helpful. For example, for certain applications in graphics and game programming, which is a real-time problem because you need to render, say, 30 frames per second or something like this. And you need to bring some order in your pixels, say a bullet moves or some object moves, but all you're generating or rendering is a frame, and 30 milliseconds later, you have the next frame. So maybe that frame does not need to look perfectly, but we need to render it very, very quickly and then have another frame 30 milliseconds later. And what was argued is, especially if you bring in some order in computer graphics and game programming, where not every frame matters too much, but the real time matters, and that maybe something is not perfectly sorted in one frame, but maybe 5 frames later, that's enough, especially if it's just a few pixels. And what you can do is you don't need to run the bubble sort until it terminates, but maybe you do a few passes of the bubble sort. So the inner loop, you do a few passes on the data, generate the frame, and then run another few passes. And so the bubble sort is helpful, say, for data sets that are almost sorted, or where you quickly need to bring in some order and maybe a little bit later bring in order again. And this was argued on the internet, and that bubble sort would be very helpful for this kind of stuff. And it's true. And this not only makes sense, but I talked to one of my contacts who was a graphics programmer at Apple, and he said that's exactly what he figured out many, many years ago. I mean, he has been retired now, and they use this kind of technique. that from one frame to another, you bring in some almost sorting into the pixels. And it's something you wouldn't have been able to do, say, with a quicksort or a merge sort, but rather a few passes, or maybe even just a single pass of the inner loop of the bubble sort. I know these are special cases, but they exist. And so if you have a data set that is almost sorted and you maybe don't want it fully sorted, but better sorted, maybe just a pass or a few passes of a bubble sort could help a lot. And that would be insanely fast. And you don't need recursion and this kind of stuff. So also your memory footprint could be very little. So we use Python in this course, and what kind of sorting is used in Python? So we have implemented quicksort and merge sort on our own, and even though these are initial implementations, they are still extremely slow. Maybe the complexity is fine, but say if you look into a professional implementation of these algorithms, there are people, they spend their whole career on tweaking quicksort a little bit or tweaking merge sort for some specific data set or for some type of data. And people do their PhD and this kind of stuff. So, people spend their whole life just on sorting algorithms. And if you use Python, there's a sorted function, and I'll show you in a moment how to use it. And what is in there, or what was in there, say from version 2.3 on, was an algorithm called timsort. It was implemented by Tim Peters in 2002 for the Python programming language. And it's derived from a merge sort combined with an insertion sort, and that was designed to perform well on many kinds of real-world data sets. And the worst case was O of n log n, the average O of n log n. It's stable. Space is O of n. Best case is O of n. So even if it's maybe the same worst case complexity as a merge sort, for a lot of real world problems, maybe this was faster by a constant factor or a certain factor. And while we ignore constants and lower order terms in our O framework, they still matter in terms of the actual running time. So maybe this Tim sort had lower constants, lower order terms, and therefore proved to be helpful. So people spend maybe their whole career on just such stuff and then maybe tweak it to use some specific features in the operating system or in the CPU, maybe to, I don't know, sort three integers efficiently. I don't know. So some people spend their whole life on this. And this Tim sort was used for a long time. And then in Python version 3.11, which came out a few years ago, Tim sort was replaced by a power sort. And it also belongs to the family of merge sort algorithms. And it's a so-called adaptive sorting algorithm designed to optimally exploit existing order in the input data with minimal overhead. So that's something that our bubble sort, as we saw it, would already do. But this was somehow integrated into a merge sort. And this one has replaced the Tim sort because the Tim sort had a suboptimal heuristic merge policy. So both derived from merge sort, but this power sort, it appeared some 20 years after the Tim sort, has a worst case of O of n log n and a space complexity of O of n and is stable. I think it's important that both are stable. And I told you quicksort is not stable, but there are also stable variations of quicksort. And just a little bit more coding, say, how can you do sorting in Python? Say, we had our data set from here before. What you can always do is sorted is a function that comes from Python, and it can sort you your data set. However, if you have more complex objects, you may have to specify which criterion to use. So imagine I have a data set that are tuples, say red, So a string and an integer. Um, then, so blue is 1, red is 2, and blue is 2. And how can we sort something like this? Well, we don't really know. So what we can do is we can specify which of these entries would matter. And for example, in Python, there's an operator module, so you can import an item getter. And when we sort our data, we could say, what is the key? So which element in the entry is the key? And we can say, well, the item getter should look into an element which has multiple entries, and within the element, look into index 1. So index 1 would be this one, this one, this 2, because index 0 is the string. So we could sort this based based on the integer. We could, however, also reverse this and say this is sorted in an ascending order. So 1 and 2, we could reverse that order and in a descending order. So the 2's and then the 1, for example. So this one here is super powerful. This would be this power sort. And it has this key parameter, it has this reverse. So overall, it's a very helpful function implemented in Python that you can use. Then we're done with the sorting chapter. Next week, there are there are a few updates for next week. The first thing I want to briefly say is the coursework. I see some people have done phenomenal progress in the coursework, and some have already submitted their mandatory problem, which is cool. You need to submit it until end of June, so there's plenty of time. So this is exercise P13.50 in the Goodrich book. And some have already started working on the exam bonus. And here I need to say a few words about it. The exam bonus refers to problem 12.6. And problem 12.6 is here in the course worksheet. 12.6 is something around decision learning. We have not discussed it yet. So if you don't know decision tree learning, don't start yet. One person submitted like problem P12.6 from the Goodrich book, which was some merge sort implementation. And I wrote that person that that's the wrong problem. Because here I wrote problem, I didn't write P minus, so 12.6, and I have not referred to the Goodrich book. So the exam bonus problem has nothing to do with the Goodrich book. And for the one person who made this submission of some other problem has still plenty of time to work on it. We have not discussed the decision tree learning yet, and there's still some time. And also, when you submit your Jupyter notebook, don't submit the Jupyter notebook. You need to export it as an HTML. And I had shown this in the first lab session of the term and recorded that. So make sure you don't submit like an HTML ending of your Jupyter notebook. I need a proper HTML. I don't need code or anything. And you can very easily extract this from Jupyter as an HTML. If you don't know how to do it, just look up the recording from the first session. And then next week, we have a special setting. So next week, we have at 10 o'clock a guest lecture from Ramon, and he will talk about AI agents for software development. And I had sent you this already in iLearn, and you're all supposed to be attending the guest lecture live. I will stream it from the lab next week, Friday at 10. You can join online as well, but I would be glad if students are in the lab, at least some, the more the better, and the others join online for the live stream. So you can ask questions and interact with Ramon. So he works at Google, and he will tell you more about how he has become more productive using AI agents for software development and why you still need to know the foundations like algorithms and data structures. And what I want to know from you is, since I would be glad if you're on campus at 10 o'clock for the guest lecture, which will be online because Ramon lives in Zurich, but I would be happy to see many of you for the guest lecture. Would it help you if we do the regular lecture next week on campus in the morning, say from 8 to 9:30, then have a quick break, and then the guest lecture and stream it from the lab? So if you want that the lecture next week takes already place in the morning at 8 to 9:30 from the lab on campus plus streamed as usual, maybe send a thumbs up. If you don't want that, if you want a lecture late in the afternoon, a thumbs down, and I would just look at the majority vote here. So I only see positive votes. So we will do the lecture then on campus from 8 to 9:30. I will send an update in the next few days, next Friday. And then you can have a quick break and stay and join for the guest lecture that we will stream from the lab. All right. So, you have plenty of time now until next week for revision. Maybe you can look into the coursework problems and then come to the lecture next week, plus the guest lecture. And after that, we'll have lab sessions and plenty of time to discuss any questions you may have. So have a good weekend and take care. Bye bye.